Okay, so coming to the it tutorial now. So we have acid, base, and salts, and okay, it's also going to be a very long one, but it's just basically something simple, and it's more of stories and theories. So let's just enjoy. So what acid is in human stomach? Okay, I've asked acid that thing. Okay, I hope we all know that there's an acid in human stomach, and what is the use? Actually, it is HCl, a very concentrated HCl, which helps in number one maintaining an environment for free digestion. It helps in killing the bacteria in you, or that's what the HCl in you, just to give our stomach the acidic acidic environment for some enzymes to work. Okay, so some citrus fruits taste sour. Why? It's because of acid. Acid taste sour. Okay, vinegar contains acetic acid. Aspirin is acetyl salicylic acid. Yeah, it's always somehow to pronounce. Then fluid inside the car battery also contains sulfuric acid, H2SO4. Then vitamin C is what ascorbic acid. Milk of magnesia, which is taken to soothe an upset stomach, is base is a base rather, which is magnesium hydroxide. So we notice that acid and base are these compounds actually have a very strong this thing to do with what with life. We use them in our what daily life activities and all. So let's move on. Sodium hydroxide is sold in supermarket under the name lye, and is also present in oven cleaners and drain cleaners such as Drano. Okay, ammonia is present or found in cleaning products around the house. Phosphoric acid H3PO4 is used in the manufacture of fertilizer, detergents, and various soft drinks like the colas. Moving on. So acid, the properties of acid, all these things are just something you just still try and relate with. So acidic compounds give food sour taste. That's what number one thing you should know. For example, the sour taste of in lemon juice and vinegar is coming from the acid they contain. Vinegar contains acetic acid. As in vinegar, we have the acetic acid, and in lemon we have the citric acid. So acid dissolves in that's that's what's very important to note about those two guys. Vinegar is what acetic, lemon is citric. Shey you get? So just don't forget for lemon, because lemon is citrus. You get? So you have citric acid, while vinegar is what acetic acid. So acids can also dissolve what active metals such as zinc and iron. Very important. That's actually because of the reaction between these active metals and the acid. The active metals will displace hydrogen away from acid, just like they also displace it from water. So aqueous solution of acid will conduct electricity, and those are referred to as electrolytes. Very important to note. Aqueous solution of acid they are good conductor of electricity when they are in their aqueous solution. So acid will also turn litmus red. I did not say turn litmus paper from blue to red. Of course, that's true, but whichever case you have, there is also litmus solution. When you put acid in a litmus solution, it will turn red. If it is litmus paper now, it also turn red. So it cannot turn a red litmus paper to red, of course. It should definitely be a blue one. Do you get my point? Just know that what acid turns litmus red. So the properties of bases now. So they are compounds that react with acid to form salt and water only. They also help in neutralization of acidity of acids. That neutralization reaction. Acid reacts with base to form a neutral compound. What's the neutral compound again? Is water, not the salt. Very important to note. So in fact, the major product of neutralization reaction is what? Is water. For example, milk of magnesia, which is a base, helps to treat the problem of excess acid in the stomach by what type of reaction now? Neutralization reaction. Aqueous solution of base have bitter taste. Uh, that of acid, they have what? Sour taste. Aqueous solution of base feels slippery. Like for the Yoruba guys, oh yo, she gets it feels slippery, just like the acids. They can also act as strong and weak electrolytes, of course. Electrolytes in the sense that they can conduct electricity. So recall electrolytes are the molten or aqueous solution that use hydrated ions to conduct electricity. So they turn litmus blue, yeah, just like acid, the way acid turns litmus red, litmus solution or litmus paper. So looking at bases now, they are base, they are bitter, and they also turn litmus blue, the big ends. Okay, moving on. So acid and bases now. So a lot of this is like a story behind it. I just had to. add its story there for you to always remember how everything went. You get. So a lot of chemists now wants to relate the properties of acids and base to their composition and molecular structure. So Arrhenius, my guy, Svante Arrhenius in 1859 to 1927. Not the name, not the year. Shey you get. So led the way, was the first person to actually kind of give us something like the first tell us about us acids and base, and that's actually because of the inception of electricity. So he was the first to start the whole discussion on acid and base, although other guys came up years after. Okay, let's move on. So four guys later gave theories that bags acid and what and bases up. So you get four. So it is four guys, but we have three theories. Four guys give three theories. That means Arrhenius, Bronsted, Lowry, and Lewis. If you know Bronsted Lowry before, it's just two guys that did that work. Sure you get. So no, Bronsted and Lowry are two different guys. They both worked together in 1927. Sure you get. So and they gave us the same theory. So that's why we just merged the two of them together. Bronsted Lowry theory. Okay. So Arrhenius now. Let's start with Arrhenius. So from 1889 to 1927, they have studied the electrical conductivities of solutions when the structure of an atom was even unknown. They don't know how an atom looks like, but they know that solutions also conduct with electricity. They started studying it. So the solute of a solution capable of conducting electricity were called electrolytes, while those that will not were what? Non-electrolytes. Chemists observed that those solutes which are electrolytes cause depression in freezing point of the solvent. They cause what? Depression, like reduction in freezing point of solvent. So it was even argued that the property, which is the reason freezing the depression in the freezing point there, is related to the number of particles in the solution. For example, KCl causes twice. We have Ka plus and Cl minus, which accounts for two particles. That's why it's causing twice what the expected freezing point depression. While calcium chloride is what? It's causing three times thrice the expected freezing point depression. That means potassium chloride causing twice, and then calcium chloride also causing what? Three times. So this is actually what now gave them an insight, because for potassium chloride to cause twice, how does the solution move? That means potassium chloride split into two. It's splitted into two rather. Why for calcium chloride is splitted into what? Three. CaCl and Cl. Shey you get. So that they already now know that, oh, that means these guys they dissociate in what? In solutions. In when they try to dissociate in solutions. Do you get my point? So moving on. This now made Arrhenius say that electrolytic compounds dissociate into particles, yes, when they dissolve in water. He said some can dissociate into two, while some three, and like that, four at times. So he said this constituent part must be electrically charged. That's it. Because we already know that all those salts they are what? Neutral. Abi now, because they are from anion and cation. If they now dissociate, that means they are going separately. That means they will take their charge back. They will definitely be charged. So then use this to explain concept of what? Acid and base, although they didn't accept it then. So that's the Arrhenius theory of acid and base, but they didn't accept it there. So although this his idea of electrically charged solid particles were not readily accepted, and which they almost ignore, like they almost ignore it. It pained our it pained Arrhenius. But after some decades, when J. Thomson discovered what negatively charged electrons in 1890s, Arrhenius idea gained acceptance. And then they say, oh, so now these guys we have charge. You talk, she get my point. That's when they now refer back to Arrhenius. We shall hope the guy never die. she get. So he received what 1903. No, that means he did not die. For him to receive the Nobel Prize, 1903 Nobel Prize in chemistry for his theory of what electrolytes. So imagine what they've been studying in 1900. Uh, all is well. So let's move on. Arrhenius now define acid as substance that produce hydrogen ions in aqueous solution. That's the definition. That's the definition we have for Arrhenius acids now. They produce what? Hydrogen ion when they dissolve in what? Aqueous solution. Because they have it. They have the hydrogen ion in them. Do you get my point? So note that the H plus also called a bare proton. You can just say hydrogen ion or a proton, because in H plus the only thing we have is a proton. It has lost its electron and it does not even have any neutron. So the only thing in H plus is what is a proton. So this H plus will be hydrated in the aqueous solution to form hydronium ion, which is H3O plus. So H plus H2O is giving us what? H3O plus. This is a more precise designation than H plus, because the H plus is in what? Is in a solution. So you cannot tell me it is still H plus, whereas you what? H3O plus. So we have examples of this acid like HNO3 aqueous, HCl aqueous, H2SO4 aqueous, HCdPO4 aqueous, and others. The aqueous is very important. That was what he gave us, that it is only after they dissolve that they will dissociate, right? So that's what Arrhenius told us then. And his limitation is also that he was restricted to the fact that acids will what? They need to be in aqueous solution before they can be an acid. You get my point? So note that all compounds that contains H are Arrhenius acids, and also not all hydrogens in an acid are ionizable. That's another point to note. In a way such that when we have an acid like HCl, the HCl will ionize into H plus and Cl minus. That means HCl is ionizable. All the hydrogen left HCl. But when you're not looking at CH3COOH, it will only ionize to form CH3CO minus and H plus. That H3 that you have in CH3CO minus is still there. Sure, you get my point. So there are still some H in CH3CO minus, but not all these were ionizable, while all the H in HCl got ionized. So the H is the H attached to highly negative atom forming a polar bond will be what? Ionized. That's the idea. It is the H that is involved in the what? Ionic bonding most likely that will ionized. Moving on. So the strong and weak acids now. So what's the strong acid? What's the weak acid? So basically it's just simple. For strong acid, they ionize completely. For weak acid, they ionize what? Partially. So acids that all the hydrogen in it are ionizable are called strong acids. And why those that all the hydrogen in it, not all the hydrogens in it are, it is not all the hydrogen in it that were ionized. Those ones are called what? The weak Arrhenius acids. So for the strong ones now, we can have monoprotic and diprotic. Monoprotic in the sense that, don't forget, proton is what? Hydrogen ion. So monoprotic means it has one ionizable what? Hydrogen ion. Diprotic means it has two ionizable what? Hydrogen ion. So for monoprotic, we have what? HClO4, which is the perchloric acid. That's the strongest acid uh, you can have. So then we have hydroiodic acid, hydrobromic acid, hydrochloric acid, HNO3, the nitric acid. Everything must be in aqueous state for what? For Arrhenius, for it to be an Arrhenius acid. And for the diprotic acid, we have H2SO4, another guy still. So those are for the strong Arrhenius like acids, the strong ones, because they ionize completely in solution. Then hey, thank God I remember this. You notice that HI is here, HBr is here, HCl is here. HI is, don't forget, iodine, bromine, chlorine, fluorine, they are in the same group. As you are moving from fluorine downward like that, their acid, the strength also increases downward. That means hydroiodic acid, HI, is the strongest of all those guys. Do you get my point? Why HF is even a weak acid? That's that. I just had to bring that in. So we can divide this. Okay, I think I already did that already. Monoprotic and diprotic. Okay, I think this is for weak. This is actually for weak. All these guys you have there, they are for weak acids. And okay, we can divide it into two parts. Sorry, I wrote strong and weak. It's just weak. It is just weak. Um, Let me change this now. It is just weak. So we have this. Okay, good. So it's just weak. Weak Arrhenius acids. Moving on. Classification of what? Hydrogenous acids now. Okay, I think we've discussed some. We've discussed the strong and weak, and you know that it is strong if it ionizes completely, it is weak if it does not. Then The monoprotic, diprotic, and triprotic is just from the idea of what? Proton. The hydrogen in you. How many hydrogen in you can you donate? That's what? The proticity. Then we have oxy acids and what? Non-oxy acids. So for oxy acids or oxygen acids, they are not that contain oxygen. Non-oxy acid will not contain oxygen. So the non-oxygen acids are what? HCl, HCN. There's no oxygen. While the oxy acids is what? HNO3, H2SO4, H3PO4, and all those guys. They can be weak or strong to sharp. So for bases now, if acid are the one that will donate hydrogen ion, base will donate what? Hydroxide ion. That's the idea. So a compound that contains OH minus known as hydroxide ion and which release some or all of this OH when dissolved in water. It is also in water again, like it must be in aqueous solution. Then we call it an Arrhenius base. So you have examples like NaOH, everything must be in aqueous state. Then in acids, the H plus is written first. Okay, yeah, but you notice that for your acid we have HCl, all those guys like that. But for in base now, your OH is last. You get. So a weak Arrhenius base like AlOH3 will have a low solubility in water, which makes it release only few of its hydroxides. Shey get. So for bases now, their strength depends on their solubility. If you are very soluble, that means you dissociate very well. The same thing for the acids too actually. Shey get. When you are very very soluble means you dissociated well. That's just the idea. So the low solubility made us put S indicating solids after the gas. So okay, I think I've explained that even in the formal tutorial. So note on Arrhenius theory. His definition of acids and bases are limited to aqueous solution using water as a solvent. Let's note that. One obvious advantage of his definition is that the role of water as solvent is recognized. The role of water as a solvent is recognized. That's one thing to note. Moving on. So Bronsted-Lowry theory of acids and bases. They are two separate guys with the same contribution. I think I said that already. So and what they both is it is actually because of what we have from Arrhenius, that is the limitations. Because okay, let's look at this. Let's say for example, when bottle of concentrated ammonium and hydrochloric acid are opened and put beside each other, fumes. That means the just like the gas of ammonia and hydrochloric acid, they'll be coming out. She get. And those fumes, if you put them together, they will still react. Do you get my point? Those fumes, if you put them together, they will react to form ammonium chloride. She get. So it will not be like it is just like okay, look at this now. Above the bottle is smoke consisting of some crystals, NH4Cl, which be a product of the reaction between fumes of the two gases. So we have this. The product we have here is same as that when we are going to use this when the solutions are mixed. If you are mixing the solution, you are trying to show the Arrhenius acid and the Arrhenius base. But the products we have for the Arrhenius acid and Arrhenius base of those two guys, aqueous ammonia is actually NH4OH. Please note that. Aqueous ammonia is NH4OH. You have to note that. So the products we have in the case of the gases and the aqueous guys, it's the same thing. It's just that the water that we used initially also came out. So do we now say this the first those are reacted as gases, they are not acid? No, they are. So you get, they are definitely acids, but their indication state, they will not be Arrhenius acid again. So it is now Bronsted and Ladin and that gave us the idea that even if you are not in aqueous solution, you can also still be an acid. So you get. So since the two reactions give the same product regardless whether a solvent is present or not, they are both acid base reactions. So you get. Hence Arrhenius can explain this whether it's an acid base reaction. Okay. So in 1923, oh, I said 27, it's 23, please. In 1923, these two guys gave us more general definition independently, like on their own, and they were not even together. She gets. So they gave us they came up with the same theory. She gets. It's like they were doing it together. So they now define an acid as a proton donor and a base as a proton acceptor. What's a proton donor? Something donates that donates what? A proton, which is H plus, while a base proton acceptor. Sure you get, that's just the idea. Yeah. And from the reaction there you notice that a proton is you notice that a proton is transferred from HCl to what? NH4Cl. Let's look at that. Yeah, we have what NH4. See, it's just like kind of NH3 before, but when you transfer that H into NH3 rather, you form NH4Cl. That's the idea. So moving on. In a procellary acid-base reaction, okay, this is talking about the conjugate acid-base pair. Very, very important concept to know. In a procellary acid-base reaction, the original acid gives up its proton and becomes a conjugate base. That means if an acid, don't forget, acid is a proton donor now. If it donates that proton, what does it become? It becomes a conjugate base of the acid. Shall you get? So then, don't forget, it is donating that proton to something, to a base. So the base, if that base accepts that hydrogen, now becomes what? A conjugate acid. Do you get my point? The one that donates becomes what? Conjugate base, because it has donated its hydrogen ion. That means it can take it back. That's why it says now a base. But it's a conjugate base of what? Of an acid. You get? While the one that accepts is normally a base before, but because it accepted, I'm busy, please. So because it accepted the proton, it became what? Um it accepted the proton, it become what? A conjugate acid, because it can now donate that proton is accepted. I think I explained that there. The original base acid accepts a proton and becomes a conjugate acid. Hello, I'm coming. So, as it can release the newly acquired proton, that's the idea. So, in other words, for every acid there's a conjugate base, and for every base there's what? A conjugate acid. Please let's note that. Then you should also note that the difference between an acid and a conjugate base is the proton. Don't forget, it is just one proton. People make the mistake of, okay, what's the conjugate base of H2SO4? She get, they now remove all the two hydrogen there and say it is SO4 so minus. No, the conjugate base will be what? Just HSO4 minus. She get, it is just a proton that is the difference between them, not two proton, not two hydrogen ions. So the same thing applies to base and its conjugate acid. Moving on, the conjugate base H2SO4 will be the guy formed after H2SO4 loses a proton. She get, look at, that's what the example I just cited. So we have HSO4 using one hydrogen ion to form and what? To form HSO4 minus. So that HSO4 minus is what? Conjugate base of what? H2SO4. Simple stuff. So it is only just one that it leaves. So then, because we now still have H in HSO4 minus, it can still use that H, right? That means HSO4 minus, that is a conjugate base, can still even act as an acid, but it will not be a weak acid. And then when it loses that second hydrogen, it now becomes what? SO42 minus. Now, so you get SO42 minus is now the conjugate base of what? HSO4 minus. That means if they say what is the conjugate base of H2SO4 and you see SO42 minus, that would be wrong, because SO42 minus is the conjugate base of what? HSO4 minus, not H2SO4. So then the reverse of conjugate acids. The conjugate acid for HSO4 minus will be H2SO4, yes, because it's kind of gain the proton, shey you get. And if it's the base, don't forget, the conjugate base after gaining a proton will form an acid. That's the idea. So HCl is the acid, while the Cl minus is the conjugate base. Okay. Note that perchloric acid is the strongest acid. So what will be the conjugate base? It will be ClO4 minus after losing a proton. So the question is now, okay, will it be a weak base or a strong base, right? Yes, it will be a weak base. Why? How do I know? The conjugate base of a strong acid is a weak base, while the strong conjugate base of a weak acid will be what? A strong base. It's just like that. So then the conjugate acid of a strong base will be what? A weak acid. So again, because the base you are using to form it is strong, then the conjugate will be weak. That's just the idea. So the conjugate of a strong is always weak, while the conjugate of a weak is always strong. So moving on to the last theory now, which is Lewis theory of acid and base. So the Lewis theory states that an acid is an electron pair acceptor, while a base is an electron pair donor. Let's note that an acid is an electron pair acceptor and a base is an electron pair donor. So a Lewis acid is joined to a Lewis base via a coordinate covalent bond, because if you remember the chemical bonding lecture, what is coordinate covalent? One atom donates two electrons that they use to bond, and in Lewis acid this thing, the base donates electron pair while the acid just gains it. So you get my point. So that means the bond in that the bond that Lewis is kind of trying to explain here is what the because some acid they don't even donate or gain proton at all. It is just that it is just the electron pair that they are transferring. So we will not say they are not acid or base. Do you get my point? So that's what Lewis brought in. So coordinate covalent bond. So examples are formation of ammonium ion from ammonia gas. Sorry, that's not. It is from. So sorry for that. For Lewis, yeah, it is from. So formation of ammonium ion from ammonia gas and hydrogen ion. So we have ammonia gas which has what a lone pair and it can donate it, while hydrogen has nothing. It cannot even like it can only accept it. She get so then ammonia will be the base, hydrogen will be the acid. That's just the idea. Hydrogen ion rather will be the acid. So the same thing with H3O plus and formation of H3O plus, which is coming from water and hydrogen ion. So water has two lone pairs, while hydrogen ion has no lone pair. So the two lone pairs is what makes the water the Lewis base, while the hydrogen ion will be the Lewis acid. And most of the time when they ask you, is this a Lewis acid or a Lewis base? For a Lewis acid, she get for a Lewis acid or Lewis for a Lewis compound actually she get yeah, for a Lewis compound it is most likely going to be what a charged particle she gets. That's just it. So moving on to salt now. So salt is a compound formed when all or part of the hydrogen ion of an acid is being replaced by metallic ion or ammonium ion. A salt is not just a product of neutralization reaction, please. Because I just told you guys that that's not the main product of neutralization is what? Is water. Because that's the neutral guy. The salt can even be acidic. We're going to see that now. So a salt is an ionic compound consisting of positive ion and what? A negative ion. So note that salt is electrically neutral by a balance of the oppositely charged ions. Yeah. So method of preparation of salt, and this is actually very very important. Questions come out from this. So many general methods are available for preparation of salt. The method chosen for preparing a particular salt depends on to a large extent on the solubility of the salt in water. Solubility, solubility, very important. Then water soluble salt are usually prepared by method that involve crystallization. If you remember our separation technique this video, crystallization what adopts solubility, while precipitation actually doesn't. Shey get so water soluble salt are usually prepared by methods that involve crystallization, while those that are water insoluble dey use what precipitation. So the methods that we have here: neutralization to prepare some salt, and those salts will be water soluble. Then double decomposition. If they say which method is for insoluble salt, is double decomposition. Please note that. Then action of acids upon metal, action of acids on what trioxycarbonate for salts. Classification of salt now. So we have simple salt and complex salt basically. So for simple salt, it's just because we have just a negative part and a what a positive part. A simple ion, negative ion, negative, simple negative ion and simple positive ion. Shey you get. There's no coordination sphere. There's no a complex. There's no complex at all. A coordination sphere is just a sphere of kind of a dative bonding. Shey you get coordinate covalent bonding. Yeah. So there are three types of simple salt: the normal, the acidic, and the basic. The normal salt is just like kind of they are normal already. They don't have hydrogen or hydroxide ion in them already at all. Shey you get, they cannot act as acid or as a base again. So why acidic has hydrogen ion in them, while basic salt you have what hydroxyl ion in them. Yeah, we are also going to look at some under hydrolysis. We're also going to see acidic and basic salt. Those ones okay, let's just move on. We'll get it better. But refer back to this that normal salt now. For simple salt, we have three categories. Then the normal salt that does not have hydrogen ion in them, the acidic salt, that means the acid is not fully the all the hydrogens are not fully replaced. Shey you get that's the idea for this acidic. So the mixture of two simple salts are called a double salt. We have to mix two simple salts mixed together, we have a double salt. So and then and most of the time you always have two cations and what a single anion. So it is just like, okay, when you have a double salt, K2SO4 dot Al2SO4 3. That's a double salt. Although the general formula they now give to it is what? KAlSO4 2. That A should be in uppercase. That would be autocorrect or something. So K2SO4 dot Al2SO4 3. That's one formula for it. Or you just call it KAlSO4 2 because we have two SO4 actually. So you get. Then I said for iron 2 ammonium tetrasulfate 6, try to work on the formula and drop it on the group. There is a bonus for the first person to drop actually. So then the second classification, which is what complex salts, they have coordination sphere. That's the idea. That means there's dative bonding in them. So and you are going to be having seeing a complex structure like you will be seeing score brackets and all. So I said another assignment now. Um, drop 5 complex salts, just 5 of them before 6 p.m. today. So then moving on to hydrolysis of salt. So salt is a compound formed by the neutralization reaction between an acid and a base. It is formed, shey you get, but it is not the major compound. Yeah. They generally ionize in water, furnishing cations and what anions. Shey get, like when they ionize, they give us what cations and the anions. So the cations and ions are formed during the ionization of salt, either exist as hydrated ions in aqueous solution or interact with the water to generate what acid and base. It's just like for example na sodium chloride. You put sodium chloride in water, you can have it as sodium ion and what the chloride ion. So for sodium ion in water, it will interact with the OH in water to form sodium hydroxide, and the chloride ion will interact with the hydrogen ion to form what hydrochloric acid. They formed the acid and base that form the salt. That's just the idea. So the process of interaction between cations and ions of salt and water is known as hydrolysis of water. Hydrolysis basically means you are using water to split. Shey you get, when you put salt in water, they split into two, they ionize. That's hydrolysis. So on the basis of hydrolysis, salts are divided into 3 categories: acidic salt, basic salt, and what neutral salt. Acidic salt are those ones that it is not that it is because they contain hydrogen ion. No, this one is just because they are acidic by nature. They are, in fact, they are normal salt. Let me put it that way. They are normal salt. Other simple salt, you have normal, acidic, and basic. These guys are normal salt. Shey you get, but under the normal salt, we now have acidic part of it. Acidic because it has low pH, basic because it has high pH, then neutral because the pH is 7. So these categories are okay. I think that's what I just explained. So hydrolysis of something or that. So let us now discuss the different types of hydrolysis we can have. So sort of strong acid and strong base. When you put sodium chloride in water now, what do you form? You have sodium chloride and what? Hydrochloric acid as the acid and base that forms it. That's the sort of strong acid and strong. In fact, let me give you this hint. The strong acid you should have in your head. There are many strong acids, but for the common sorts and questions you can see, the strong acid you should have in your head is H2SO4, HCl, HNO3. There's those 3 guys. While for the strong bases you should have in your head is just 2: KOH and NaOH. Every other guy is just take it to be weak. Although you know that there is ClO4 is also strong already. Shey you get. HI is also strong, but you won't see those salts. They won't be testing you on those salts. Shey you get my point? So that's the idea. So and then if you have salt of strong acid and strong base, because it's strong, the idea is it's going to form a neutral salt. That's the point here. So a salt of strong acid and strong base is what is a neutral salt. That's the point I want you guys to bring out from this. Then salt of weak acid and strong base, because it's this base that is strong, it will be a basic salt. That's just very, very basic stuff. And then you have this. Look at that. CH3CONA. It is coming from CH3COH and what? NaOH. NaOH is strong. CH3COH is not strong. She is a weak guy. So we have what? A basic salt being formed. Then salt of strong acid and weak base. If you guess what, to be what? Acidic in nature. And that's what? NH4Cl. That would be what? NH4OH and HCl. HCl is strong, NH4OH is not. Check it. Then the last one, sort of weak acid and weak base. This one, it can be anything depending on the nature of the acid and base involved. She get, it can be either acidic, basic, or neutral. That's just the idea here. So and that depends on the Ka and Kb actually. But that's not for this class, it's actually kind of advanced. But let's just notice that way. Although if you now see question on it that okay, weak acid and weak base, just pick it to be what? Neutral. Just like the way strong acid and strong base also what? Neutral. So that's all for this lecture.